Hi everyone, my name is Andrei Schwartz. I am a lecturer at the James Watt School of Engineering at the University of Glasgow, and I am one of core developers of MoFEM. I want to talk briefly today about a few PhD projects that we've been currently running at our group. So first of all, what's MoFEM? MoFEM stands for the Mesh-Oriented Finite Element Method, and it's essentially an open source parallel finite element library. And it has a wide range of multiphysical applications. You can learn about these at our website. You can see the link over here, but you can also scan the QR code on the left to access the website. Okay, before actually talking about the PhD projects, I want to make it clear. Why do we want to invest our time into developing an open source research finite element library when there are so many commercial codes available? Well, I guess we enjoy doing it thanks to the inclusive community of people who develop and use MoFEM, and as you can see, it's growing from year to year. But our key advantage is that we implement advanced finite element techniques. So we use high order approximations. We have error indicators which enable automatic refinement, and we use such formulations as mixed or hybrid methods, which are deeply rooted in some sophisticated math. And thanks to these finite element techniques, we can sometimes solve the problems which commercial codes cannot solve. Or quite often, we can solve it faster or more accurately than the commercial codes. But in addition to that, thanks to this advanced finite element techniques, the system of equations that are built in our code are very much capable of being effectively run in high-performance computing environments. And I'm not talking only about the CPU clusters. I'm also talking about GPU, and we've been investing quite a lot of time recently to make sure that our system of equations are GPU-friendly and are prepared for the emerging architectures. Furthermore, we don't try to reinvent the wheel, and when there are some nice tool already exists, we make our code compatible with them, and this includes some popular pre- and post-processors for the meshes, solvers for the systems, material libraries for integrating material behavior, and then notebooks and cloud platforms. And finally, to make our work more efficient and sustainable, we use some elements of professional software development. Git for version control, various package management tools, some other tools for automatic testing, and so on. Okay, so now I just want to come to actual projects, and I hope I will be able to show you not only the depth, but also the breadth of the projects, because as I was saying before, the code has a very wide range of applications in engineering. So the first one over here is Adriana, and she is currently finishing her PhD project in civil engineering. And she has been working on addressing uncertainty in the material behavior in advanced gas-cooled reactors, which are operated by EDF Energy. So she in particular was implementing data-driven modeling in MoFEM. And by using material data in simulations and also controlling finite element errors, Adriana was able to quantify uncertainty of the results and also identify when the data is missing or of very low quality. And this has applications to the problems of irradiated graphite bricks in AGRs. Right, so these are some of the results. And okay, the next project is done by Tanzib Ehsan Sanglap. He is a PhD student in mechanical engineering, and he is using MoFEM for modeling and optimization of TENGs. So TENG stands for triboelectric nanogenerator. And these are very modern devices, which sometimes are called autonomous clean energy harvesters, because they can transform mechanical energy into electrical energy. And thanks to their wide applicability, the sources of the energy vary from maybe some wearables to large-scale ocean networks. However, optimization of these devices is required, and Tanzib is looking into the intricate coupling of mechanics and electrostatics, and in particular, he's doing simulations to figure out how the surface roughness in these devices affects their performance. Okay, here is Yingjia or Leo, who's doing his PhD in electronics and electrical engineering, and he's looking into modeling chips in MoFEM. So basically, he's developing a semiconductor simulator, and he was to address multiphysical phenomena in chips, such as electrical, thermal, and mechanical coupling, at the same time taking into account the heterogeneous structure of chips. And the main goal over here is to optimize chip design for advanced packaging. And the last over here, but definitely not the least, is Cai. And actually, he is doing his PhD in a different school and in VLS. And his PhD is in cancer studies. But what he's actually doing is very close to biomedical engineering, and that provides the room for our collaboration. Cai is looking into the mechanical characterization of post-infectious changes in the guts of a fly. So he infects flies, then he cuts the gut open, takes out some portion of the intestinal tract, and then he performs non-indentation experiments on them. He obtains some data in form of the forced indentation curves with the goal to figure out if the infection changes stiffness of these tissues. And the problem here is that he obtains poor fitting of his data using simple analytical models. So that's why Cai is using MoFEM to run simulations and extract mechanical properties of the samples with a much higher precision. All right, so having shown you the breadth of applications, I just want to finish by mentioning that we've recently created a startup company. This is currently led by Karol, who is also a former PhD student in the MoFEM group. And the idea of the startup is to leverage MoFEM capabilities for industrial clients. And Karol has already landed the first project. It's on the virtual environment, VR environment for surgical training and planning. And this project is in collaboration with the Queen Elizabeth University Hospital in Glasgow. And the main idea over here is to create an integration layer for VR using MoFEM simulations in the high-performance computing server. So the goal over here is that the surgeon would be able to upload scans of a patient and then assemble the shattered bones in the VR environment with their own hands, run the simulation powered by MoFEM, and grab the results and figure out if they are holding. So once the confirmation is obtained that the chosen assembly is working, after that, surgeons can get out of the VR and perform the real simulation. Okay, I hope this short list of applications was interesting for you. Like I mentioned before, you can navigate to a MoFEM website to see more cases and more projects. And if you have any questions, feel free to get in touch. Thank you. Bye.